All right, continuing on, let's talk a little bit more about black holes. Now, this isn't in the book, but I'm just going to lay out some stuff for you, stuff for you to ponder. So, all right, so here's our black hole. And at the center of this black hole is a singularity. This is what the math tells us. The math tells us that let me get that a little bit more centered here. About there. Okay. All right. The math tells us that the mass that has collapsed from this neutron star has gone down to this single point. And like I said, this makes physicists crazy, but this is what the mathematicians say would happen. And here's where one of the problems comes from this. When we talk about mass density, that equals mass over volume. So many kilograms per cubic meter. And we've already talked about this in other contexts. If we reduce that denominator, this quantity gets bigger. That's just basic math from 4th grade. And if this denominator approaches 0, this number approaches what again? Infinity. And so if you have something of so much mass, but the volume is 0, what's the density? It is infinite. And the physicists say, what the hell is infinite density? That doesn't even make sense. And like I say, the math guys say, you're the physicist, you figure it out. That's what the math says. So we're getting into wacky land here. Inside this black hole, the escape velocity is greater than c. This is something you've probably heard about. I should put this over on the other side of the board, actually. Over here. That is the event horizon. What is the event horizon? That is the point, that's the geographic location, if you will, of where escape velocity equals the speed of light. Anything outside that event horizon, escape velocity is less than the speed of light. This is referred to as the Schwarzschild radius, named after a German physicist named Schwarzschild. He was an artillery officer in the German army during World War I. Now, if you recall, this is about the time when Einstein had published his theory of general relativity, which talks about how gravity works. Schwarzschild, who was a physicist in civilian life, was reading this work, and he applied what Einstein had to say about gravity to this idea. And so this radius is named after him. That's the Schwarzschild radius. Now, we always go back to Newton. Remember, we calculate escape velocity this way. Now, what if we stipulate that escape velocity is the speed of light? All right. That's useful. Let me show you why. First of all, how do you unsquare something? How do you unsquare root something, rather? Well, you square it. So we're going to square both sides of this equation. And now we get c squared equals 2gm over r. basic algebra tells us we can swap these. And now we get this. That, ladies and gentlemen, is how you calculate the size of a black hole. The Schwarzschild radius of a black hole is equal to 2 times the gravitational constant times its mass divided by the square of the speed of light. You're going to want to remember this one. You will see it again. You will see it again. One last thing. This is referred to as a Schwarzschild black hole. But there is another type of black hole, and I should also hasten to add that what we are talking about are stellar black holes. Black holes that were born of individual stars. We're not talking about supermassive black holes, but individual stellar black holes. There's 2 basic types. This is a Schwarzschild type of black hole, and there's one other type in which the black hole is spinning and it has kind of an oblate form, and that means that the singularity is spinning as well. This is called a Kerr black hole. And some weird stuff happens with a Kerr black hole because as it spins, it drags space-time right along the event horizon. The gravity is so intense at that point that space-time itself gets dragged along. The way to imagine it is, imagine fudge being stirred in a pot, and you stir that ladle in the pot and you can see the fudge getting dragged along. This is what happens with a Kerr black hole. It drags space-time along, and that space-time drag is referred to as an ergo region. All right. Do jot this stuff down on blank paper because I will be talking and asking you about it down the road here. But that's the basic outline of a black hole. Oh, I want to show you one other thing too, while we're at it. You can go to any number of sources, online or in a textbook, in which you will see a black hole described like so. In this case, we're talking about the curvature of space-time, which we covered in special and general relativity. So the sketch will show something kind of along this idea. And you'll see a grid, and then you'll see this funnel type depiction pointing toward the singularity. This kind of, when you think about it, this kind of contradicts what we're saying here. Because from the outward view of a black hole, remember, this is why relativity is so important. We, as the observers outside a black hole, are going to see this. But the interior of a black hole, that's different. What we perceive its radius to be from our vantage point outside the black hole is not going to be what its radius is within the black hole. Look how it's stretched, and conceivably going down to infinity. So for those of you who are Doctor Who fans, Now we truly have an object in which the inside is bigger than the outside. Food for thought.